be responding to them throughout the seminar. And without further ado, I'd like to pass this over to John. Welcome, John.
Thank you, Dave. And first, I'd like to start by thanking not only Dave, but the whole team at IMW for giving me this opportunity to speak to you guys today. It's a privilege and an honor, and I hope you guys learned something that you can take back to your day-to-day function and help you out. So to get things started, I'd like to give everybody a quick overview of Cook Compression. Those of you who may not be familiar with us, Cook is a worldwide leader in the component design and manufacture of critical parts for reciprocating compressors. We also offer monitoring and repair solutions as well for existing equipment in the field today. So the markets we cater to include natural gas, both upstream, midstream, and downstream, petrochemical and refining, enhanced oil recovery, and industrial markets. So basically anywhere where you can find a reciprocating compressor, Cook is going to be there and have expertise in that particular application. Cook Compression is a division of Dover Corporation, which Dover is a Fortune 500 company, over $8 billion in annual revenues, traded on the New York Stock Exchange. We offer a broad range of compressor valve, sealing, and emission control technologies for, again, reciprocating compressors. And that's going to be the focus of our discussion today, is learning a little more about these technologies. We also have a highly experienced engineering staff with expertise across all compressor products and applications. So not only can we manufacture the components that the compressors need to operate, we have the expertise in-house that's required to get them to run better, last longer, seal gas more efficiently. Lastly, we offer a line of sophisticated analyzers and monitoring systems through our Windrock product line that allow you to see inside the compressor, that monitor the internal condition, that allow you to change your mindset from preventative to predictive maintenance. So a quick overview of what we're going to cover today. First, we're going to define and give a quick overview of each critical component required to achieve gas compression. So we're going to tell you what the components are called, what they look like, and give a brief overview of how they function. Next, we're going to describe the benefits and challenges surrounding non-lubricated CNG compression. Then we're going to review Cook's approach towards extending service life in non-lubricated CNG compressors. And lastly, we're going to talk a little bit about a project that Cook and IMW have been working on jointly over the past several months that involves a standardization of IMW's product line and what the benefits will be of that change to the end customer. So let's get started by defining critical components. So I wanted to describe to everybody what we're looking at here in this slide. So this is a cutaway view of a compressor cylinder. So if you guys can notice my mouse moving around here, down here at the bottom left-hand side of your screen will be what we call the running gear, or the crankcase. So you'll have a crankshaft, a connecting rod, and a crosshead that's rotating, causing this piston inside the compressor cylinder to reciprocate. So the way the gas compressor works is low pressure gas will enter the cylinder from the top side of your screen through a series of valves. It will be compressed on both sides of the reciprocating piston, and it will be delivered through a series of discharge valves. So basically you're moving gas by compressing it, raising its pressure. So what are the components required to make this event occur? Well, first we're going to look at what we call the wiper and the pressure packing. And you can see it's the wiper and pressure packing are enclosed in an assembly that's bolted to the back side of the compressor cylinder. And the wiper packing's goal is to prevent any oil that is contained back here in your crankcase that's lubricating your crankshaft and connecting rod bearings from migrating down the rod and into your compressor cylinder. Secondly, the pressure packing is there to prevent any gas pressure that's built up in your compressor cylinder from leaking into your frame or your crankcase. Next, you have piston rings that are designed to slow the flow of gas between each end of the cylinder, so they're preventing gas leakage between the piston and the cylinder wall. Next, you have a series of compressor valves, which act as pressure-actuated check valves that allow gas to flow in and out of the cylinder as it's compressed. So We won't talk in too much detail about valves in this course. We're going to focus more on the sealing components, as they tend to be more of a critical item in non-lubricated applications. But certainly, if there's a question on valves that you want me to answer at the end, I'll certainly take those. Next item we have is what's called a rider ring, and so that is installed on the center of the piston typically, and it supports the back and forth inside the cylinder. So before we move on, I want to make a very critical distinction here between a lubricated and a non-lubricated compressor. You heard me talk about oil back in the crankcase that's lubricating the crankshaft and the connecting rod bearings, and that's going to be present in a lubricated and a non-lubricated compressor. But what makes a lubricated compressor different is the fact that oil is going to be introduced. You can see my mouse here, right here at a point inside the cylinder to lubricate the piston rings and the rider ring. You're also going to have an oil introduction point here in the packing case to lubricate the pressure packing, and these are the components that are rubbing and sealing. The purpose of the oil is to extend their life. However, there are some challenges certainly associated with CNG compression, which is meant for vehicle fueling when it comes to lubricated equipment. For one, you have separate pieces of equipment designed to deliver that oil to the cylinder, which involves a separate set of pumps, things we call divider blocks that divert the oil to different lubrication points, and also instrumentation involved. But the critical point to make with a lubricated compressor, the fact that once that oil enters the cylinder, it is going to be absorbed in the gas stream. It's not like your oil back in your frame or in your crankcase that's being constantly recycled. This oil is lost into your process gas. Eventually it's going to go out through your discharge valves into the gas system, which creates some real challenges when it comes to a vehicle fueling application, which is one of the things that makes IMW unique, the fact that all their compressor cylinders are non-lube, meaning there's no oil introduced into the cylinder or in the packing, and all the seals run completely dry. So we'll get started with a little more detail here on pressure packing and wiper packing. So we'll start with the pressure packing case. And as I mentioned before, the pressure packing is contained in an assembly. And the assembly consists of a series of metallic cups. So usually cast iron or steel is the material of the cup. And within the cup, you'll have a series of packing rings. And the rings can be made of a variety of both metallic and non-metallic materials. And the function of the packing case assembly is to seal high pressure gas and prevent leakage from the cylinder into the frame or atmosphere. So if you can notice my mouse here, in this example, all your gas pressure would be contained right here on the top side of your screen. So in a CNG compressor, that could be anywhere from 20, 30 psi in the cylinder all the way up to 4,500 psi. And on the back side of your packing assembly, you're going to have atmospheric pressure. So what we know about high pressure gas is it's always going to seek a low pressure source. So you're relying on the packing assembly to keep that gas in the cylinder. Within the assembly, the packing rings are what are doing the sealing work. So they seal around the rod and against the packing cup to prevent that gas from migrating down the case assembly and out into the frame or the crankcase. The assembly is sealed against the cylinder with an end gasket. So when you install this device, you have this end gasket right here where I'm pointing with my mouse that seals the entire cylinder off, packing assembly off against the cylinder. And lastly, the rod rings are going to be pressure actuated seals, meaning that they rely on the presence of gas pressure to cause them to seal against the rod and against the packing cups, which we'll describe in further detail here in a couple slides. So this is a breakdown of what the assembly looks like taking apart. And so what we're trying to illustrate here is for the folks out in the field, the technicians who service compressor equipment, the rings are going to be what wear out over a period of time. And so when you're doing maintenance on the compressor, you can take the entire assembly out, take it apart as shown here by removing nuts on the end of what we call the tie studs. And these tie studs, you can see, go all the way through the cup stack to hold everything together. Once you take this assembly apart, the individual rings contained in the cups can be removed and replaced and easily put back together and thrown back into the unit. So typically the metal parts are either reused or repaired, and the rings are what's replaced during maintenance. So how does all this work? So we know that we could possibly have a high level of pressure in the cylinder, and we have this little few-inch long packing case that's designed to take that pressure down to zero. So to really understand what's going on inside the packing case assembly, we're going to look at some data that we took off of our in-house test compressor. And in our test compressor, we're looking at not only pressure in the compressor cylinder, but we're looking at pressure in each packing cup behind each ring set. So we're really seeing what's happening between the cylinder, where you have hundreds to thousands of psi gas pressure, all the way back here to the back of the case, where you should have little to no pressure. So that leads to the graph here on this next slide. And to give it a little explanation, looking here on the x-axis, you're looking at your crank angle. So this is telling what point in the stroke that piston's at, whether the gas pressure is low or high. And on the y-axis, you have the actual pressure number. So looking at this blue line, this is the pressure inside your cylinder. So it's cycling between suction pressure down here at about 700 psi up to about 1600 psi, which is your delivery or discharge pressure. So this next line is a red line. This is the pressure behind your first cup, behind your first ring, and this is a ring we call a pressure breaker. So all this ring is doing is monitoring or metering the flow in and out of the packing case as your cylinder moves from suction to discharge. So it's kind of smoothing out that pressure change, rate of pressure change as gas pressure changes in the cylinder. But what's of interesting note are the following data points. So this is the gas pressure behind each of the sealing ring sets. So as you can see, each ring set is slowly and little by little knocking the gas pressure down to almost zero once you get to the back of the case assembly. So in essence, this is how the packing case is functioning. All the rings in the set are doing a little bit of the work, sharing a little bit of that load in order to knock the pressure down to a manageable level to the back, at the back side of the case. And so that's why you'll see in a packing assembly you'll have several ring sets. This is also why low pressure packing assemblies have fewer ring sets than higher pressure assemblies, because as pressures get greater, we need more seals, more sealing power in the assembly in order to knock that pressure down to an appropriate level. So that's how things work on kind of a macro or a higher level. So what's actually going on inside each packing cup that causes the ring to physically seal gas? And that's what this next slide is going to illustrate. So if you can picture here in the center, this is an illustration of your piston rod. So it's going to be reciprocating back and forth as you cycle from suction to discharge strokes. The left-hand side of your cylinder, slide is cylinder pressure. The right-hand side is going to be atmospheric. So all this gas on the left-hand side of the screen is trying to rush to the right. So within this cup, this packing ring set is going to have a slight amount of side clearance. So the width of this cup, or this ring, is going to be slightly less than the depth of the groove within the cup. So that side clearance will allow the ring set to float laterally as that rod moves. And that movement creates the side clearance that allows gas pressure to fill the cup and surround the ring, which creates the loading forces required for that ring to seal gas. So for example, you see this loading force, gas pressure on the outer diameter of this ring set is creating a loading force downward that causes the ring's inner diameter to seal against the rod's outer diameter. So you can see there's a loading force right here where my mouse is moving. So any gas pressure that wants to leak down between the ring and the rod is going to be sealed off. Additionally, you have a loading force on the face of the ring that's pushing this further down ring on the downstream side of the groove up against the packing cup face, which is preventing gas from leaking around radially. So essentially that's what we mean by a pressure actuated seal. That gas pressure is creating the loading forces required for that ring set to seal gas. So now I want to talk about some different ring styles. And the previous slide was kind of a representative example. There are several different designs and materials used for packing rings. But the most common ring style that you'll see in compressors today, both lubed and non-lubed, is a ring style called the BTR. It's been around for 20, 25 years. It features a radial and a butt tangent cut ring that are typically made from a filled Teflon. So here's your radial cut ring, and here's your tangent cut ring. And you also have a backup ring on the back side of this tangent cut ring that's there to provide structural support. So without getting into too many details of the design of this ring, the key takeaway here is this tangent cut ring is doing most of your work. So that tangent ring is what is loading up against the rod as pressure fills the groove, and that's what's squeezing down and creating that loading force. This backup ring, as you can see, has a large amount of clearance over the rod, so it's not really contacting that rod surface. It's more or less there to keep this tangent ring from getting pushed down the rod. So again, I mentioned materials for the radial and the butt tangent portion are typically made from a filled PTFE, which stands for polytetrafluoroethylene or Teflon. Backup rings are typically made out of a bronze or a PEEK-based material, which PEEK is polyether ether ketone, which we'll talk in a lot more detail about materials here in a few slides. This ring set is single-acting, meaning it only seals in one direction. And for the technicians out there, to understand the correct orientation of installation, they must be installed with the letters on each face of the ring facing the pressure source. So if you can watch my mouse here, there'll be a letter on each segment of the ring, which indicates for the technicians in the field what side of the ring needs to face the pressure. So next we'll talk quickly about wiper rings. So the purpose of a wiper ring is to keep the crankcase oil in the crankcase by wiping it off the rod. You remember we talked earlier about the separation between the crankcase oiling system and the compressor oiling system, and this ring is what you're relying on to keep those two systems separate. So in the graphic here on the right-hand side of the screen, here's your crankcase. That oil is going to collect on the rod, try to migrate down to the compressor side. You're relying on this oil wiper ring to scrape that oil off the rod and drain it down through an oil return in the system back into the crankcase. How the ring works is typically there are special edge geometries, or whether it be small wiping lands or edge point of contact type designs, combined with high spring tension to allow the wiper ring to shear the oil film off the rod. So a pretty simple concept of what it's trying to do. However, it's critical in the performance of a non-lubricated CNG compressor. For one obvious reasons is you want to keep the oil out of the compressor to keep it from migrating into the gas stream. But it's also critical to the extending the service life of the other components like the packing rings and the piston rings, which we'll explain here in a couple slides.
Questions coming in here?
Yeah, John, we just had a couple of questions here. How do you develop your wear materials?
Well, that's a good question, because it's critical in the absence of oil to have a material that's designed specifically to survive in that environment. And the design of the material it really takes a lot of research and development effort on our end. So, we mentioned that the base materials are typically Teflon and PEEK, but you'll have a lot of fillers and additives into those base materials that will allow that ring to function in an oil-free environment and not only provide just standard lifetime. We want to extend that and allow that compressor to run just as long as a lubricated machine. And I do have a slide here in a couple minutes that talks in further detail about what the wear materials are that we're using today. But as far as the development process goes, it involves a lot of lab testing, in-house wear testers at our facilities. Once we qualify which materials and which blends work the best, then we'll take them out for field testing over a long haul and make sure that they give us the results we're looking for in the field.
So these final materials will be proprietary to Cook then?
Yes, proprietary blends, and over the years we've developed several dozen different blends. So that's something that we feel is something that differentiates our company, is our engineering expertise and ability to develop specific materials for specific applications.
Great, thank you.
So to move on, we'll change the topic to piston rings and riders. So in this graphic here, we'll start with discussing the piston rings, and they're pointed out here as smaller items that are installed on each end of the compressor piston. And the piston ring's function is to stop or reduce the flow of gas between the piston and the cylinder. So in this example, if you have a double-acting compressor cylinder, right here you're pretty close to bottom dead center, which means the gas pressure on the crank side of the piston is going to be very high when you compare it to the gas pressure on the head end of the piston. So again, high pressure gas is going to try to migrate its way towards a low pressure source. So you're relying on your piston rings to stop or slow that flow of gas between the piston and the cylinder. Secondly, the rider ring has a completely different function. Its goal in life is to keep the piston from contacting the cylinder wall. So it's there to support the weight of the piston and rod assembly as it moves back and forth in the cylinder. Typically there's a single rider ring. It tends to be a much wider component than the piston ring, and that's because we want to have enough rider ring surface there to properly support the weight of the assembly. Additionally, we designed special features into the rider to prevent it from sealing against the cylinder wall like a piston ring. So we have built-in leak paths in the rider ring that prevent it from pressurizing. So to give a few notes here on some typical designs you'll see out in service, usually what you'll see in a piston ring or a rider is a single piece or a two-piece angle cut design. And we'll start with discussing the piston ring. So with the piston ring, the key to the design is the joint. So there's got to be some sort of a break in the ring to allow it the freedom to move within the groove. And so picking that joint is usually an exercise in give and take. So we're trying to get the most reliable design we can that allows us the best sealing efficiency possible. And what we find is that the angle cut design is very robust, it's easy to manufacture, and it gives us good enough leakage protection in most of your applications. So you'll see that in most of your cylinders, particularly on the lower stages of a CNG compressor. Next, for the other applications that may require a little bit better leakage prevention, you'll see something called a seal joint or a multi-piece ring used in higher stages to reduce blow-by. And that's what's shown down here in the bottom right-hand side of your screen. That's an example of a seal joint design. And as you can see, the joint kind of interlocks and overlaps, creating a very tough path for gas to escape paths. So that gives us much better leakage prevention. However, as you can see also, the cross-section of this ring gets rather thin at certain points, so it reduces the robustness of the design. So oftentimes we'll use this style in conjunction with angle cut rings in order to keep the loading on the seal joint low. Additionally, this joint is a little more difficult to manufacture and it's a little more costly, so we only use these ring styles in situations where we need them.
Just about 3 questions that popped in here.
Okay.
So just thought I'd ask them. Eric has asked, generally, how often do the seal rings need replaced?
Well, that is a very good question that doesn't have a single answer. Generally, the target is the 8,000 to 12,000 hour range. Those numbers can be influenced by a number of factors, including the cleanliness of the gas that you're pumping, how well your machine's aligned, what gas pressures you're operating at. But if you select the correct materials and the correct designs, you should be able to get a year of runtime, if not more. That's typically what we shoot for.
Okay, so Bob asks, what prevents the rider ring from wearing in one spot due to gravity?
Well, typically it will wear in one area. It is, going back to this slide, gravity is the force that's acting on the rider ring. So it's the bottom side of the ring is taking the brunt of the punishment. What we do is through a calculation that we make, we determine how wide that rider ring needs to be in order to properly support the weight of the piston. And so we're trying to keep that bearing load under 5 psi for a non-lubricated application, and that's the industry standard that gets us acceptable life. So basically, the heavier your piston and rod assembly is, the wider that rider ring needs to be to properly support the weight and keep the loading down.
Now, I've got one question here, and I'm just struggling with some of the wording here, so maybe you'll be able to answer it for
Okay.
me. But the question, the way it's worded is, and it's from Javier. It's, can we use piston rings PTFE in a hardness, I think it's meant to be hardened cylinder?
So we're looking at the hardness of the cylinder. Depending on the hardness, I don't see any issues using a PTFE. The key that we look for in the contact surface isn't necessarily the hardness, it's more the surface finish. So we're looking to keep that within a 12 to 18 RA finish to allow the transfer film to properly develop, which is something we're going to discuss here in a couple slides. But the hardness isn't our big concern, it's the surface finish quality.
Okay, that's it for now. Thank you.
So next note on riders, typically they'll include side notches, and it's kind of tough to see, but if you look up on the top upper right-hand portion of your screen, you can see where I'm mousing over an example of a side notch, and what that does is that prevents the rider ring from loading up like a piston ring. So any gas pressure that builds under the ring will be relieved through the side notch. And again, typically filled PTFE or PEEK-based materials are common for piston rings and riders, certainly in non-lubricated service. Again, on the lower pressure side, we use the PTFE as it's higher availability. It's very good, lower cost. It wears pretty well. The higher stages, you'll need to upgrade to a PEEK, which has better temperature and pressure resistance. However, it's more expensive, so you don't use that as universally as you would PTFE. So next slide, we're going to talk a little bit about non-lubricated CNG compression in particular. So we're going to talk about the benefits and the challenges that surround this particular application. So first, we'll go through the benefits. If we all remember from a few slides ago, in a lubricated compressor cylinder, all the oil that's injected into the cylinder is going to be absorbed by the gas stream, meaning in a CNG environment, the possibility exists that that oil is going to make its way into the fueling system of the vehicle, and that has a very negative effect on the performance of the engine, both from a performance and an emissions standpoint. So going back to the source where the oil is coming from and eliminating that and going to a non-lubricated compressor helps to eliminate this concern. Next, reduced operational costs due to reduced oil consumption. So again, in a lubricated compressor, all your oil is essentially going to be lost to the gas stream, so you're constantly having to replenish your oil supply, which adds cost, and that cost is not there in a non-lubricated environment. Next item is reduced capital and operating expenses from the elimination of equipment required to deliver and handle the compressor oil. So we talked a little bit about the equipment required to deliver oil to the compressor cylinder, the pumps, the divider blocks, all the tubing and instrumentation involved there. There's a cost to that, both upfront and ongoing through maintenance. And secondly, if you have a lubricated compressor, you got to find a way to get that out of your process and on the delivery side. So there's coalescing filters and things like that are required in a lubricated CNG compressor skid that aren't required in the non-lube application. So next, what are the challenges surrounding a non-lubricated CNG compression? Well, first, from a sealing component standpoint, again, the packing rings and the rider rings and the piston rings, the elimination of lubrication increases heat at the sealing surface and can reduce the life of the rings if not properly accounted for. And heat is a big thing for a packing and ring manufacturer. It is the #1 item that causes the life cycle of the parts to be reduced. So we're always looking at ways that we can reduce the amount of heat generated at the sealing surface, and we have some special designs that help us do that we'll talk about here in a couple slides. Another challenge are space constraints. CNG packages tend to be as compact as possible. That's certainly, we don't want to take up any more footprint than we need to. And from a packing side, that can be a challenge. Because sometimes we would like to add features such as water cooling to the packing ring or to the packing case that allows us to pull more heat away. That's not really an option in a CNG application due to the complexity and the envelope concerns that system would create. So we've got to find other ways to get the heat away. Next, our high linear piston speeds and high pressures at the upper stages increase heat at the sealing surfaces. So one of the things we're looking at from a heat generation standpoint is pressure. If you remember the slide where we showed the rod ring being loaded up against the rod, well, it's being loaded up by gas pressure. And the more pressure in the environment, the harder that ring's squeezing, the more heat is generated. So with the CNG application, the pressure is pretty much fixed at that 3,600 to 4,500 PSI range. So as a packing and ring designer, we have to find ways to get our components to last in that environment. Lastly, close coupled frames create challenges for wiper seals. And so to define a close coupled frame, that would be in a situation where the crosshead would come just right up to the backside of your oil wiper packing. So basically there's no distance or distance piece in place to separate and keep that oil splash to a minimum. So special considerations need to be made to keep that oil wiper from getting overwhelmed with the amount of splashing going on inside of your crankcase. So that's another consideration that needs to be taken as well. So you may be thinking, wow, look at that long list of challenges. How do we get good service life out of a non-lube compressor? Well, I can say that, certainly through experience of IMW and Cook Compression, we have several decades of experience with excellent service life in this type of application. The key is to take the proper considerations, both in the compressor design and in the component design, to make things, to set things up to work in this environment. And I'll give you an example of some folks who tried to get the benefits of a non-lubricated compressor skid without taking the proper precautions. So what these folks did is, and we've heard several stories of this instance taking place, where they went out and bought a lubricated compressor, decided they didn't want to deal with the oil anymore, and they just shut off the oil supply to the compressor cylinder. Well, those folks didn't run much longer before they had a major failure on their hands. For one, their compressor components weren't set up for non-lube, and two, the compressor itself was not properly designed for a non-lubricated application. So it didn't have the proper baffling in place to block the oil source. The speeds were too high. The piston wasn't long enough. It just was not set up correctly. So for that particular end user, they were pretty disappointed with what they got. But again, it requires upfront design and engineering, both from the compressor and the component standpoint, to achieve a good service life out of a non-lubricated CNG compressor.
John, we've got a couple of questions here. Chris asks, how do expander ring sets function differently? I have seen sets with steel expanders on low pressure, higher diameter pistons. Yeah, that's the question.
Okay. Well, what an expander does, and I'll go back to the slide that shows piston rings and routers, is it is a device that is installed underneath the inner diameter of the piston ring that expands it outward against the cylinder wall. So a piston ring functions kind of in the reverse direction of a packing ring. It's using gas pressure to push it out against the cylinder wall. And where we would use an expander is when the pressure differential across the piston is very low. So that means there's not enough energy there to properly load up the piston and cause it to seal against the cylinder wall. So that's where we'll go to an expander ring. In lubricated applications, we'll go with steel, but most of the time in non-lube, we try to keep the metal out of there, so we'll go with some sort of a plastic like a PEEK. But again, the function of that is to load that ring outward, create an additional force to push that ring against the cylinder wall.
And Nico asks, does the ring change on different stages? I mean, when it comes to material and sizes or specs?
Yes, it sure does. On the lower stages, you're typically going to see angle cut designs made out of a filled PTFE-based material. That's just to keep things simple, and that Teflon's readily available, lower cost, and it will give you the performance you need at those lower stages. Using a higher end material like PEEK there would be overkill. However, as pressures get higher in the 3,000, 2,500 PSI range, you've got to go to a material that has better temperature resistance and higher strength, so it can withstand the environment. So that's when we'll go to a PEEK-based material, and oftentimes we'll change the geometry of the ring, going to more of a seal joint type design, due to the fact that those higher pressures are more prone to leakage. So yes, you'll see the design of the rings change from cylinder to cylinder based on the operating conditions.
And one last one before I let you continue. What is the maximum RPM of non-lube compressors? I assume it's lower than a lubricated unit. That's from James.
Well, that's also a good question. The industry standard's about 750 feet per minute, so it's not really an RPM calculation. It's a linear piston speed calculation based on the stroke and the RPM. Have we pushed the limits beyond 750? Absolutely. But getting, again, the faster it runs, the more heat's going to be generated, the less life you're going to get. So staying in that 750 feet per minute range has proven to give long life and reliability time after time after time. So
okay,
we tend to stay in that area.
Great, thank you.
No problem. So let's go back here to the next slide, which is a little information on Cook's approach towards non-lube CNG component design. And so what we were really looking for to extend the service life of these machines is a combination of upgraded materials and proper design as being the key towards extending service life. And we feel this is something that separates us. We're not simply looking at throwing an upgraded material into the machine and to gain higher service life. Certainly material selection is very important, but what we feel is a separator here that's going to take us to the next level is the product design. So we're looking at designs that not only generate less heat, but remove more heat from the sealing surface. So we're trying to keep that heat off the sealing surface. We're trying to reduce oil carryover through wiper design, and combining that with upgraded and engineered materials is going to give us the best life we can possibly get. So now moving on a little bit into material selection. So the challenge that we're up against is selecting a wear material to survive in the absence of oil. You know, if you can picture a lubricated surface, it's not all that difficult. You know, you've got that oil there to give you a cushion, and that's great for wear part. But for the reasons we discussed earlier, oil is not something you want in a CNG application. So from our standpoint, we're looking for a material that will lay down what we call a transfer film on the counter surface that it's sealing against. So if you look at the graphic on the right-hand side of your screen, this counter surface represents the rod. And you can see it's kind of a wavy surface, and that represents the microscopic surface finish on the piston rod itself. So while it may look smooth to the naked eye, within the surface of the rod there are peaks and valleys. And so what we're doing with the transfer film, shown here coming from the base material, is for the first few strokes of life, that base material, which would be the ring in this case, lays down a layer of itself into the peaks and valleys of the counter surface. And that material film then adheres to the counter surface and creates a self-lubricating and lubricated environment. So the ring is basically running against a layer of itself, which therefore extends its life. And that's our challenge, is to find a material that will lay that transfer film and run for a long period of time against a layer of itself. And in order to do that, as I mentioned a little bit earlier, we have an extensive materials development program that requires lab testing and field trials to get that proper blend of material. You know, again, PTFE and PEEK are the base materials, but the key is in the fillers and the additives. To get this transfer film to behave the way we want it to, we have to get that right blend of the right amount and the right type of filler. And that's what separates our proprietary materials here. Another note on the last bullet here is that oil carryover will wash away this transfer film and accelerate wear. And this is one of the reasons why wiper performance is so critical in a non-lubricated application. Because any oil that gets on that counter surface is going to pick up that transfer film and wash it away. Well, but what that means is the base material's got to lay another transfer film, and then another, and another. And very quickly you'll see that material wear out in a hurry and cause a shorter than expected service life.
I was fascinated to hear earlier when we were discussing the impact that this has on maintenance process and procedure, in that in a typical lubricated compressor, as you're doing an overhaul, you literally soak the materials, if you will, in oil. Here, it's as far the opposite way as you can get, where you would strip any possibility of oil out right down to the point of using surgical gloves to avoid human hand oil transferring.
Absolutely, and that kind of leads into the next slide, where cleanliness is very critical in performing maintenance on any non-lubricated compressor, to make sure that any oil, whether it be from your finger or from an outside source, is not in contact with any of the sealing surfaces, to allow that transfer film to properly develop and adhere to the counter surface, and that's very critical. And not only when we build the assembly in our shop, but when packings are rebuilt out in the field technicians need to be aware of that as well. So the next slide gives you a list of some common materials found in non-lubricated CNG piston rings and packing rings, and it kind of gives you an evolution of where things started. Carbon-filled Teflon was really the first non-lubricated material, and it's fairly common, lower cost, gives decent performance in the lower pressure realm of things. However, it does not lay a very good transfer film in the absence of moisture. So in dry gas applications, this material doesn't work very well at all. So that kind of evolved into a polyimide filled Teflon, which if you guys have ever seen the rings that have a yellowish tint to it, it's likely that's polyimide filled. Gives better performance than carbon filled Teflon, but it was the industry standard a few years ago, but it's been kind of superseded today. And so that leads into filled PEEK materials, which are commonly used on the higher pressure applications. So again, PEEK being the base material, special fillers being used to allow that PEEK to run in a non-lubricated environment. And that's what you're going to see today on the higher pressure cylinders, anything in the 2,500, 3,000 PSI range and higher. So lastly, we get into to today's top-of-the-line material, which is called TruTech 3330. So this was developed by Cook over several years in lab and field testing. And it's a PTFE-based material with proprietary fillers to allow the transfer film to be developed and to last for a long time in both wet and dry gas applications. So it's really got a very broad range of where we can use it, and certainly in the non-lube CNG compression industry, it's a very good choice. And so we're going to talk about that as it applies to IMW compressors here in a few slides. And the next two bullet points we already covered about making sure cleanliness is paid attention to during maintenance. So next we're going to talk about product design. So again, what we're looking to do from a sealing component standpoint is to reduce the amount of heat generated at the sealing surface. So first, let's try to understand where the heat comes from inside a compressor. First thing you got is compression of gas. So that's when you squeeze a gas, it gets hotter. That's the laws of physics. So what we can do about that is make sure that the compressor is sized correctly and the pressure ratios are adequate enough to keep that discharge gas temperature in a relatively low range, somewhere between 250 and 300 degrees Fahrenheit. Next, you have friction of the piston rings in the riders as they ride against the cylinder wall. And lastly, you have the friction of the packing rings. And so this is what occurs when that gas pressure causes the ring to squeeze down against the rod. And this is what we're going to try to address with specific product designs. And so that leads us to today's best available technology for packing rings, which is something called Uncut or solid ring technology. And what we call this ring, we have as the designation for it of a BTUU. So you remember the BTR from an earlier slide. A BTUU consists of a radial tangent ring pair, just like the BTR, but what makes this ring unique, the patented use of two uncut backup rings, which are solid with no gaps, no springs, that they have a small amount of clearance over the rod. And as gas pressure builds in the cup, those rings will collapse down against the rod and aid in the sealing process. And we were able to manipulate when those rings close down against the rod by careful material selection. So what are the benefits of this style of ring? First is lower gas leakage in both running and shutdown conditions. Field testing has shown that gas leakage has been extremely low after several thousand running hours with this ring design. We have a flow meter that will go down to below 0.05 standard cubic feet per minute, which is a very low leakage level, and we've found that this ring after several thousand hours, can still hold a leak rate that is too low for that flow meter to pick up, where a BTR ring set just simply could not do that. Next benefit is reduced friction, and this is the big thing that's going to extend the service life of your ring. So reducing friction lowers your rod temperatures and extends service life. It also includes better sealing that requires fewer ring sets. So we're in the example before, a BTR ring set sealing 2,000 psi of pressure would require 4 to 5 rings. We can do that in 3 rings with the BTUU. So that shortens our design envelope, allows us to make a more compact offering. So the next slide shows you really how these rings load up. If you remember from our discussion with the BTR, essentially one ring's doing all the sealing against the rod, and that's the tangent ring. As you can see in this graph, you're looking at the cylinder pressure changing on the y-axis and the piston location changing on the x. As the gas pressure in the cylinder cycles from suction to discharge, the loading within the ring set changes from the tangent ring down here at low pressure. Once your cylinder pressure reaches a moderate point, this first uncut ring collapses against the rod and picks up the sealing load. The last uncut ring closes down as the pressure reaches discharge and picks up the sealing load. So essentially you have 3 rings sharing the load compared to just 1 within the BTR ring set. So everybody remembers this slide from earlier showing how the BTR ring set breaks down the pressure as you move through the cup stack. So as you can see, you have 1, 2, 3, 4 rings here that are depicted that are knocking down that gas pressure. Well, let's compare that to the same test using a BTUU ring arrangement. So you can see here the cylinder pressure in the first cup, which is the pressure breaker, doesn't change. But you look here at the remaining cups, it's almost 0 pressure. So basically 1 BTUU ring set is doing the job of 4 BTRs. And that's really what helps us keep that heat down. Because if you can picture that BTR ring set, all 4 of those rings are squeezing the rod, creating heat and friction. The BTUU, you've got 1. So what does that mean? Take a look at this next slide. This is again taken off of our test compressor. You look at the discharge pressure here on the x-axis increasing, compared it to rod temperature on the y. With the conventional packing arrangement using BTR sets, your temperature on your rod is anywhere from 290 up to 310 degrees Fahrenheit. Compare that to the BTUU, you're about 100 degrees Fahrenheit cooler. What that means for the life of your packing is extremely significant. We hear reports in the field that the BTUU will last 50 to 100% longer than a standard BTR type ring set. And so this is the technology we're moving forward with IMW to help give the end customer the best available service life out of their machinery. So next, quick note on wiper rings. We have a special design there called an RTV. And this type of ring features a proprietary joint design that is meant to reject the oil before it gets into the groove. It also has a side-loaded gas sealing element that keeps gas from leaking into the crankcase, so it helps us reduce the overall design envelope. So last couple of slides here. First, I want to talk to you a little bit about a project we've been working on with IMW that involves a standard compressor lineup. So what this means is, in the past, where IMW compressors have been more customized for a particular application, we're moving away from that towards a standard product range of pre-designed cylinders and component designs that are going to be used for new compressor assemblies. So what this means is we're looking at this kind of a blank slate and making sure that we include best available sealing technology for non-lubricated CNG compressors. So we're looking at things like BTUU seals that include optimized materials that allow us to work very well over a full range of operating conditions. Next, we'll look at a series of custom designed piston rings that use joint designs and materials that minimize wear and blow-by. And while I say custom, they'll be custom for each cylinder. However, that cylinder will be the rings assigned to that particular cylinder will be standard. And what that does for us is that condenses the available number of configurations and the number of parts down to a minimal number. For example, we're looking at only having 2 different BTUU unique ring sets that cover the entire range of operating conditions. So what that means for us is if you're out in the field and you need a spare set of rings, since there's only 2 available ring sets, there's a very good chance that either Cook or IMW is going to have that set available for you, which is a big benefit for spares planning. Additionally, the lead time of the equipment is going to be much shorter since the packages will be pre-engineered. And lastly, the design envelope is going to be much shorter. Since we're using this the BTU style seals, we're able to compact that packing case, which allows benefit in the compressor design as well. So to wrap things up, I'll go over some key takeaways here. First is that high service life can be achieved in non-lubricated CNG compression when the proper considerations are taken. So again, simply turning off the switch on a lubricated compressor is not going to get you the results you need. You need a machine that is custom designed to work in a non-lubricated environment. Next, the enemies of compressor components are heat and oil carryover, so especially in non-lube applications. So to maximize life, we're going to use a combination of product designs and wear materials that are specifically aimed for reducing heat generation and limiting oil carryover and minimizing wear rates through proper material specification. Next, cleanliness precautions are critical during maintenance to promote proper material transfer film development. So again, that goes back to making sure that you're cleaning off all the sealing surfaces and not introducing any oil into the environment. And lastly, standardized IMW compressors will utilize best available technology for the components with the goal of achieving high service life, low lead times, and high spare parts availability. So any questions?
Excellent. Okay, John, I do have a couple. I'm wondering, but while we're asking them, Tim had asked, would you please show the solid ring again?
Okay.
The slide went by a bit fast, so while you're going there.
This one?
I believe that. Hopefully that's it, Tim. And Jermaine asked, do the rings perform better and longer in cold weather than in very hot climates, or is it irrelevant?
The climate doesn't have as big an impact as you would think it does, again, because most of the heat in the environment is due to the local conditions. So what a hot environment would do, it may increase the gas temperature being introduced into the compressor and may increase your suction temperature, which will in turn increase your discharge gas temperature. But the majority of the heat we're concerned with is the friction generated at the sealing surface, and that's not going to be as impacted as you may think by the outside environment. Gotcha.
Tim was hoping you could go a couple of slides earlier there. Apparently, it's a couple of.
This one?
We'll see if that's the one. While we're waiting on Tim there, several folks have asked will we be able to receive the slides, and we will be sending a survey email next week, and it will include links to the slide deck. And we'll also be editing and posting this webinar on the IMW website, so you can certainly access it there. Now, Tim is acknowledging, yes, that's the correct slide, but how do you get it on the rod?
Well, you have to use a neck-down thread design, meaning that the diameter of the threads on the piston rod must be smaller than the diameter of the main piston rod sealing area. So you would have to install these rings into the packing assembly, install the assembly in the back of the cylinder, then plunge the rod down through your cylinder and in through the packing ring. So maybe if I back up here to the component slide. So basically what you'll do is you'll install this assembly here first where my mouse is floating. So all those rings will be kind of held in place. Then you'll take the piston rod and install it right down the middle of this packing assembly. Now you'll use a device called a thread protector over the rod threads to keep the rings from getting damaged. But by having that thread diameter that's smaller than the main diameter of the piston rod, it's able to slide in through those uncut rings.
Excellent. Now, David has asked an excellent question, which I'd asked you earlier. We've got an IMW 50 built in '05. Could we get these new packing systems to improve our machining performance? And just to put this into perspective, David, Cook is working with our manager of research and development on this project. This has been a co-development effort, and I'm sure John can speak to this more. These products have not been fully tested yet. We have 5 test sites where we're undergoing the prototype versions. When they are released, yes, they will be, as opposed to our friends at Microsoft, they will be backwards compatible. So you will be able to retrofit your previous IMW 50s with the new technology. Anything to add to that, John?
No, I think it's once we get it done on the standard units, we can go back and retrofit a design for any compressor out in the field today. So that's certainly something we can do. Okay.
Now we're exactly 1 minute over, but we did start 1 minute late, so we'll grab a few of these questions here while folks are still able. Are there any considerations for the compressors with low usage, i.e. long periods of inactivity? Doug asked that.
I think the main concern there would be preservation of components, making sure that if you're down and you're not pressurized for an extended period of time, it may be worthwhile to take the components apart and make sure that no rust is built up anywhere in the system that could interfere with the sealing components. But as far as I guess it would depend on how long you consider to be a long shutdown. If you're just up, maybe at a 25% utilization, you're down for a day here or there, not a big deal. But if you're down for months at a time, then you may want to consider taking things apart and re-inspecting before going back online.
Okay. Ahmed asks, what about the effect of intermittent lubrication due to wear in the oil wiper? Is there a material that can work halfway between lubricated and non-lubricated cylinders?
Well, certainly you're kind of in that environment where oil is carrying over. The transfer film gets washed away. So that intermittent lubrication is probably the worst case scenario for any ring material. Because if you're running completely lubricated, you don't have to worry about a transfer film. But once that oil goes away, the film is laid. Well, then here comes the lube back due to the poor wiper performance, knocks the transfer film away. So to answer the question about is there a better material, yes, there are materials that run better than others in that environment. But I think our approach to that would be let's attack the source here and find out why the wiper is not performing the way it should, and let's fix the wiper so we don't have to, put a Band-Aid on the sealing rings and get them to survive.
Now it looks like your comments earlier on in your introduction have piqued Ivan's interest. He asks, what are the tools that we can use for predictive maintenance?
Well, our Windrock product line gives the end user an ability to see what's going on inside the compressor, and I'll stay at this slide for an example. So what that would typically involve are pressure and temperature transducers that are directly introduced into the cylinder. So you can see the rate and the pressure changes and the pressure drops across the valves, how much leakage is blowing past your piston rings. You can really look at that data that's being taken inside the compressor cylinder and use that to determine, A, is your compressor performing like it's supposed to? Is your flow and horsepower and everything like that in line? And B, are there any problems with any of the components? So you can pick that up by looking at these pressure and temperature traces, and also looking at vibration at different points within the compressor itself. So, for example, if a valve went out, you could pick that up with a vibration trace at a specific point in the compressor. So it allows you to really see, rather than just saying every 10,000 hours I'm going to tear my compressor down and change parts, it allows you to change, do maintenance as is actually needed versus doing maintenance as is unnecessary.
Okay. Well, we are out of time. We've gone a little over. We want to be respectful of those boardrooms full of engineers out there. So I have had multiple questions. Where can we get the slide deck? Again, there will be a survey coming out early next week. There will be a link to the slide deck. In addition, we will be editing and posting this entire webinar on the IMW website, and we invite you to pop in there and see it. For those of you who have a few questions that are popping up here at the very end that we just can't attend to, please feel free to contact myself or just send an email to sales@imw.ca. That's sales@imw.ca. And if you reference the webinar and your question, we'll be happy to get back to you and work with John on that. Thanks very much, John. We really appreciate it.
No problem, guys.